For answer is demystified. I'm going to talk about Beard-Lambert's law and its application in anesthesia. So when we look at the Beard-Lambert's law, the intensity of light traveling through a known substance reduces proportionally to the concentration of the substance and the distance it travels through. So the absorption is equal to log 10 of the incident light over the transmitted light and is equal to a constant called the epsilon or the extension coefficient, the distance or the path it travels through, and the concentration of the substance. Now let's look at these two laws separately. In the Beer's law, we have a substance of known concentration in a beaker. When we shine a light through this beaker, certain amount of the light will be absorbed by the substance and the intensity recorded on the other side is reduced. Now if we increase the concentration of the substance, the amount of light absorbed is further increased and the recorded intensity is reduced further. So if you look at Beer's law, it states that the intensity of parallel beam of light decreases exponentially with concentration C. As the concentration of the substance increases, the amount of light absorbed is increased proportionally. Now let's take two beakers of different sizes but containing a substance of the same concentration. When we shine through a light through the first beaker, a certain amount absorbed, the intensity recorded is reduced. But when we shine the light through the larger beaker, the amount of light absorbed is reduced further and the concentration recorded is much lower than the first one. And that's because the light has to travel through a longer distance. So Lambert's law states that the intensity of parallel beam of light decreases exponentially with distance or length it travels through. So in simple terms, Beer's law relates to concentration. Remember beer. Beer is alcohol, different concentrations of alcohol in different drinks. Lambert's law starts with L. It is a lengthy name, has to do with the length or distance the light travels through. Now let's look at the application of this law in capnography and gas monitoring. Now, these laws are used in infrared spectrometry. Infrared spectrometry basically states that the interatomic bond between dissimilar atoms of molecule absorb radiation in the infrared range. So substances like nitrous oxide, which have two dissimilar molecules, carbon dioxide, anesthetic agent which has got different molecules of carbon, of hydrogen, of the bromide, chlorides, fluorides, water which has hydrogen and oxygen will absorb infrared light, but nitrogen and oxygen or helium will not. So if you look at the absorption spectrum of the certain gases we monitor like carbon dioxide, it's maximally absorbed at 4.26 micrometer, anesthetic agent at 3.3 micrometers, nitrous oxide at 4.5 micrometers, carbon monoxide at 4.7. Anesthetic agents are also absorbed at the further range at 10 to 13 micrometers, so 3.3 and 10 to 13 micrometer range as well. So if you look at the gas monitors, they consist of infrared source which transmit infrared light at 1 to 15 micrometer, and this light passes through a sample chamber, and it also passes through a reference chamber. Then we have a filter wheel which rotates at a frequency of 25 to 100 Hertz, and it has got filters for carbon dioxide at 4.26 micrometer, anesthetic agent at 3.3 micrometers, nitrous oxide 4.1 micrometers. It can also have a second filter at 10 to 30 micrometers, and then the light passes through detectors and then the display. So the amount of absorption of infrared light is proportional to the substances that are present in the sample. And you can see the absorption spectrum. But what is important is that in the range of 3 to 5 micrometer, the absorption spectrum of carbon dioxide, nitrous oxide, and carbon monoxide is very close by. And this leads to something called collision broadening. So the nitrous oxide, carbon dioxide, anesthetic air, water, they all actually absorb the heat, and they can affect the absorption of each other. Water is present in abundance in our breath, and that's why we actually have filters for not filters, but there is a chamber which actually collects the water in this chamber, which does not go to the analyzers, so which is taken off from this. But it's not just the substances which absorb infrared light that can cause the collision broadening. And non-infrared absorbing substances like helium, argon, acetone, alcohol can also affect these measurements. So we have to be careful. Now, if you look at heliox, sometimes used in patients with difficult breathing, which contains oxygen 79% helium, it also affects the capnography. Capnography is going to underread if you're going to use heliox in these patients and monitor the carbon dioxide levels. Then we look at another system that uses Lambert's law, that's pulse oximetry. So if you look at the pulse oximetry, there are two parts to pulse oximetry. First is the plethysmograph that measures the pulse, and then comes the oximetry, the saturation, which we are very concerned about. That's what we look at. The pulse oximeter usually use two wavelengths, 660 nanometers and 940 nanometers. Whereas the co-oximeter use a range of wavelengths, so they're more than that, and they're able to monitor the carboxyhemoglobin, methemoglobin. But with the standard pulse oximeter, we only look at oxygenated hemoglobin and deoxygenated hemoglobin. And for the exam purposes, you should be able to draw this line. So what you do, you have a graph x-axis wavelength nanometers, absorption on the y-axis, and then you put down the values for that, 600, 700, 800, 1000, and then you draw a tick mark. And then that is for oxygenated hemoglobin, and then a hills and valleys, and that is for the deoxygenated hemoglobin. Then you draw a line through 660 nanometers, that is the red range, so maximum absorption of the deoxygenated hemoglobin occurs here, and 940 nanometers where the oxygenated hemoglobin is absorbed. The point where both the absorption is equal is known as the isobastic point, and this is around 800 nanometers. So we all know that in a pulse oximeter there is a probe which sits across the thumb or the fingers, and on one side we have the source of light which transmits lights at 660 and 940 nanometers, and on the other side is the receiver. And this information is then fed to the pulse oximeter. Now, how does a pulse oximeter give us that reading of 97-98%? And that is very, very important. And to understand that, we need to understand something called AC and DC components. So when we look at the finger, what we have is that we have the pulsatile component, which comes mainly from the arterial blood. But the non-pulsatile components not only comes from the venous blood, but it also comes from the other tissues. So light passes through this pulsatile and non-pulsatile component, and this is detected. And so we have the measurements at 660 nanometers and 940 nanometers, and this is the raw transmission signal. What the pulse oximeter now does is that it needs to equalize the numerator or the DC component. So they are made equal, and then we look at the ratio of absorption at these two wavelengths. Okay, so we look at AC 660 by DC 660 and AC 940 by DC 940, and this gives us a ratio called absorption ratio, the R, and this is plotted on a graph. And there we get the values. When the absorption is around 0.6, we get a value of 97%, but when the absorption is equal, ratio is equal, we get 85%. And this is very, very important. These values are actually drawn from volunteers. And because volunteers cannot be ethically desaturated below 80%, any reading below 80% is an extrapolation. and cannot be trusted. There's limitations with pulse oximetry, and some of them are safe. They can be because of mechanical artifacts, because of movement artifacts. They can be from the interference, from magnetic interference, electromagnetic interference like diathermy, and they can be physiological. We know that if there is a shutdown, the pulse volume is low or the rhythm are irregular, and then the saturation can be affected. But these are safe limitations. But there are certain unsafe limitations we should be aware of. Like I mentioned, the calibrations occurs using the volunteers where they cannot be desaturated below 80%. So the accuracy below 80% is reduced. Flooding and penumbra can actually affect. This is seen when you actually use a large probe in a small finger, like in pediatrics. The ambient light can affect the reading, and that's why we should be sure that either the probe is covered or you use the right size probe. And then there are other physiological limitations like abnormal hemoglobins, absorbance, and pigmentation, dyes, delays, and pulsatile veins. And some of this we're going to discuss a little bit. Carboxyhemoglobin overreads because the absorption of carboxyhemoglobin is in the oxygenated hemoglobin range. It is maximum at 660 nanometers. Whereas with methemoglobin, it depends on the level of methemoglobin. So if the level of methemoglobin is actually very less, it will tend to actually still read 85%, and that means it is actually under reading. Even though saturation may be around 93-94%, it's actually under reading the saturation. Whereas if the level of methemoglobin increases very high, so if you take a sample and measure it, the saturation may be around 80-83%, but the pulse oximeter will read 85% because the absorption at 660 nanometers and 940 nanometers is equal for AC and DC component with methemoglobin. So it tends to overread when the levels of methemoglobin is very high. Fetal hemoglobin, skin pigmentation, bilirubin, they do not affect oximeter reading. And the cold vasoconstriction, vasodilatation that occurs in septicemia, they affect the plethysmography. They don't affect the oximetry. Oxygenation can still be measured. It may not be giving a reading constantly, but they affect the plethysmography, not the reading of that. Thank you very much.